Hello, I'm going to try something new today. And so what I'm doing is, in addition to the document that I uploaded, I'm going to record a video kind of walking through some of the stuff here. I try to write these documents in such a way that best imitates what my lecture would look like if I were in a classroom with a board and your student sitting there, what I would say, and anticipate what sort of questions you might have. But there really isn't a substitute for talking and demonstrating. So hopefully this will work out. And so the basic idea of a linear inequality is a linear inequality is similar to a linear equality. So here 2x plus 3y equals 12 is a linear equality, and what this represents is the collection of xy points that make this statement a true statement. So something like, you know, uh, 6x plus 0y makes that true, and 0x and 4y, or 0x is 0, y equals 4 makes that true. And infinitely many other points also make that true. X is 3 and y is 2, etc. And then when you take the collection of those points, they form a line. And so we can go ahead and graph something like that. 2x plus 3y equals 12. And boom, we see here, that's the line of points that make that true. Now, when we have an inequality, it means that, well, 2x plus 3y could be 12, but it can also be less than 12. And so this is also, solution to this is also a collection of points that make this statement true. And naturally, it's a lot. It's a ton more points than this original one. It includes all original ones and everything that's on one side or the other side of this line. And if we want to know which side, we could just pick a point on one side, like 0, 0 is pretty easy. Or plug it in. It's 0 plus 0 less than 12. Yeah. So this half is part of the inequality. This half is not. So if we change this to less than or equal to, then, right, we see that we get that half here. And so a system of equations is what happens when you have a bunch of linear equations and you're looking for the collection of points that make them all true. And so a system of inequalities is no different. If I have a system of equalities like 2x plus 3y is less than or equal to 12, x is greater than or equal to 0, y is greater than or equal to 0, what I'm looking for as a solution is the collection of points xy that make all three of these sentences true. And so it would have to lie on this side of this plane. It would also have to lie to the right of the y-axis and above the x-axis. And then the place where all three of these regions meet, that's going to be my uh, this triangle here is my collection of solutions to this system of inequalities. Now, this is really, really hard to see, right? It's at a certain point, there gets to be way too many things going on, and you really just can't make heads or tails of what's being graphed anymore. So, one helpful trick in Desmos, I'm going to deactivate all of these layers here, is you can nest the inequalities. So I could say, well, I want to graph 2x plus 3y is less than or equal to 12. But I only want the ones where the x is non-negative and the y is non-negative too. And that's much nicer, much easier to see. So we got over here our acceptable region. And so this orange triangle here, that is the solutions to our system of inequalities. And so what linear programming is the science behind given uh, a system of inequalities and some function. Here we have f of xy being x plus y. we want to find the point or points of x and y that make all three of these things true and also make x plus y as large as possible. And so over here on this tab, this is the calculator that's embedded in my website, and uh, it's set to maximize or minimize 2x plus 3y, subject to, well, kind of a long list of constraints here. So why don't we go ahead and change this to reflect um, the inequalities in our problem. So we want 2x plus 3y is less than or equal to 12, subject to x is greater than or equal to 0, y is greater than or equal to 0. All right, and so we have this thing here, and then we have this line here. Now, uh, what this line represents, let me go back here, is here's my function x plus y, right? And I want to make that as big as possible. So what could x plus y be? Well, in general, x plus y can be anything you want, because given any actual value for x plus y, like -5, say, or -6, let's just do that, right? There's going to be a line that corresponds to that, and it could be like 100 or your, 28, and that also corresponds to uh, a line as well. And so, in general, x plus y doesn't have an upper bound. What we're looking for, though, is a point in our allowable region that will maximize x plus y. So, if I try to make x plus y, for example, -1.5, this line totally misses my region. So there are no points in my region that will make x plus y -1.5. The smallest x plus y could possibly be is 0, and that's what happens when my line crosses through the origin here. Now, can it be bigger than that? Sure, right? As I make it bigger, right? If I want x plus y to be 2, boom, these are all of the points here that will make x plus y 2. But can I make it bigger than that? Yes, right? I can make it 4, and boom, here are all the lines that make x, or all the points that make x plus y 4. Can I do better than that? Yes, right? I can go all the way up to 6. This is the collection of points that will make x plus y equal to 6, and it's just the point 6, 0, right? X is 6, y is 0. That makes that satisfies all of our inequalities, and it makes x plus y have the value 6, which is the biggest value we've gotten so far. If I try to make this even bigger at all, let's say 6.01, or that's hard to see, let's say 6.1, and zoom in a bit here, um, we now note that I've moved off the uh, the region. I've moved out of it, and so now that can't be uh, a possible solution. There are no points in my green triangle that will make x plus y 6.1. And so there's two observations to make here. One is all that linear programming is doing is really pushing out the boundary of some line or some plane and seeing how far up or down we can make it. And the other thing is that my solution has to land on a corner of some point, because there's only two possibilities. Either I push it all the way out and I hit some corner, and that's the best I can do, or, and this is a bit weirder of a situation, so let's say that my bound, instead of 2x plus 3y is less than or equal to 12, is x plus y is less than or equal to 12. When I get all the way out to 12, let me just type it in. That maximal face lies right on my line, and then this corner and this corner here are both optimal solutions. So if I want to find my optimal solutions, all I have to do is check out what happens on the corners. That will tell me exactly what's happening. So on to the example problem here. Here we have a fairly reasonable um, word problem that demonstrates the utility of this sort of thing. So we have a student, and she's going to raise a bunch of animals. She can raise 16 animals at most. The costs are 25 per goat and 75 per pig, and she has a budget of $900. She doesn't really like goats for some reason, so she won't raise more than 10 goats, and she gets $12 profit per goat, $40 per pig. And so what should she do to maximize the profits? Well, first thing we want to note is that P of xy here is 12x plus 40y. That's how much profit she'll get for raising x goats and y pigs. So why don't we go over here and put those values in? 12, 40. All right. And then we probably also want to change up our constraints here. So when we look at our constraints, we say, oh, okay, x plus y has to be at most 16, right? Because she can have only 16 animals at most. Uh, she can't go over $900 in her budget. She has to have less than 10 goats. And you can't really have negative goats or pigs. So that's like our list of constraints, right? So why don't we go ahead and put that in? So we have x plus y is less than or equal to 16. Constraint 1. Uh, constraint 2 is that 25x plus 75y. Whoops. Is less than or equal to $900. All right. Um, we know that x has to be less than or equal to 10, and we know x is greater than 0, y is, or greater than or equal to 0. Y is also greater than or equal to 0. And so that's the shape of our region. And you can probably, try to eyeball where all of these corners are. But if you wanted to be precise, all of these corners represent intersections of lines. So you could take all of the lines defined here and then use whatever techniques you want to find out where they intersect, see what these 5 corners are. But it's honestly so much easier just to uh, put those lines in directly. Go 900, say x is 10, x is 0, y is 0. And that gives us all of these lines, so I can click on here. So my points are 0, 12. Let's move this thing out of the way. Let's set them equal to 0, why not? 6, 10, 10, 6, 10, 0. Yeah, you can double click on the points and it records them, although I think it only let you do so many at once. And then 0, 0, let's say. And so one can just go ahead and test 12x plus 40y on these 5 points. And really only 4 realistically. I mean, there's no way that, not raising any animals is going to be the best solution. But we could, so you can take these values, plug them in, and calculate them out. But we can even do this part lazier if we felt like it. So let's go in and insert a table with x1, y1, 12x1 plus 40y1. So I by putting, for example, 0, 0, it tells me that 12x plus 40y will be 0, which, duh, we knew that, right? What's my next point say? How about 10, 0? Here we go. 10, 0, that's 120. 10, 6, which will definitely beat 120. 6, 10. 472. And 0, 12. 480. So let's turn this off here. So if we look over on the right here, we have our 1, 2, 3, 4, 5 corners, and here we can observe all of their values, and we'll see that at 0, 12, right here, that is our optimal solution where we do not raise any goats and we raise 12 pigs. Now you might wonder, I mean, she could raise up to 16 pigs. Why would she stop at 12? Well, that's because at 12 pigs, we run into this blue line here, right, which is the bound for the amount of money that she has. So she only has the money to raise 12 pigs. She can't raise any more than that. And if we wanted to see this process, okay, so at 100 they caps out to about there, and we know we're talking about much bigger numbers here. So why don't I change that to 1,000 cap? I keep going. So and we can see the line starting from 0 as it crosses through all the different corners, right? It goes through 10, 0, and then 10, 6, and then 6, 10, and finally, boom, right there. Uh, it's hard to see visually. 472, or sorry, 472 is there, and then boom, at 480 it hits that point, right? And so that just kind of verifies what we already know, is that 0, 12, 0 goats, 12 pigs is the optimal solution. So I hope that helps. I'm happy to continue to narrate videos like this if it's something that you guys would be interested in. And also, if you have questions on homework and you wanted me to narrate a solution to a homework problem, I could do that for you too. Please let me know, and thank you for watching.